And welcome back, everybody. Today, we are going to continue on our discussion from last class, or yesterday, if you will. And yesterday, we were talking about weight, seemingly, and drag force. So, remember that weight is not kilos, it is not in pounds, it is in newtons, because weight is very specifically the force that gravity exerts on you, or that you're exerting on whatever you're standing on due to gravity. Now, moving forward through here, and I think those are my physics notes, but I could be wrong. Boom, good. Okay, yesterday we looked and saw that, hey, this Newton's second law idea that is force equals mass times acceleration is how we work out weight. And then, depending, it might be helpful in some problems. Instead of saying that meters per second squared, newtons per kilogram is the same unit. But if you're working with forces, this is the one that's going to cancel out with the mass that you're given. So more convenient, but not required. Okay, we then did a single problem where we said, hey, the weight of something is 7 kilograms on Earth. We took gravity and mass and we found it. Weight is measured in newtons. Okay, super duper important idea. Going through, we started talking a little bit about scales. Let's knock out a problem. Cool. Yeah, I'm fine with this. This is what we left off with yesterday, right? Okay. So, I like to go through when I do random problems with us. They're not random, just so you know. Poor choice of words. When we do problems together, I pretty regularly use ones that are considered as challenges, just to show that, like, if I don't say the word challenge or anything, it probably doesn't really feel like it. But here we go. We're going to knock out a problem right off the bat, and I'm going to try to be as concise as possible, and I can type it, so why wouldn't I just do that? Using a little editing magic to shorten the video, here is our problem. Here is our problem. If you're watching this video on the road, please go ahead, pause it, and take a second to jot it down, and then resume when you're ready. Okay, we're going to start with free body diagram. What am I going to use to represent the sack with stuff in it? What do you think, Mickey? How am I going to draw this sack with a bunch of stuff in it if we're doing a free body diagram? One more time. So definitely vertically. I think maybe that question could be worded differently. Are you going to draw an actual sack, like a bag on your... What are you going to draw instead? Boom, that's what I needed. Here's our bag that's full of stuff. Now, it's sitting on it somewhere, right? Because we're about to lift it upward. So it's sitting there. While we start lifting, or when we start lifting, what forces are acting on it? Okay, and gravity pulls this bag which way? So downward. Now, I'm just going to say, check it out. Here's the force of gravity, F sub G. Simultaneously, though, what else happens? It's pushed upward. Now, this thing winds up moving upward, right? So when I draw this vector for my lift, or whatever we're going to label it, longer, the same, or shorter than the force of gravity? It better be longer, right? Okay, so here it is. Here's the force, and then this is a total option for everybody. F sub what? How do you want to label this? And I used a word on mine, but what would you write? What force is this? Any objections to if we just say it's the force of the lift? Like we're lifting it, right? If you have a different option, I'm fine with it. It doesn't bother me at all. Now, in the end, just to make sure that we can try to make a little bit more sense of this, I know that it accelerates upward. So I'm just going to go ahead and add over to the side. I'm going to do one more, not specifically yellow. I'm going to do one more little dot, and vector rather. Holy cow, they're going crazy in there. And we are accelerating this way. Okay. This is what's going on. Now, there is a tricky part of this problem as compared to some of the others, which will make the others seem a little bit easier. But let's go ahead and go through our knowns. And we're going to have to be a little bit clever with it, I think. Okay. What do we know about this problem? And this is Friday morning, and it feels like a Friday morning. So I'm going to go ahead and use my calculator to help us pick. And check it out. Rafa, what do you know? Say that again. Okay, so force of gravity, we do know it. You want 9.8, I'm fine with that. And what did you want our unit to be here? Meters per second squared, I'm fine with that. Careful, that's not quite. Let's work this out here. You're not giving me the force of gravity. You're giving me something else. Because the second that we say we need a force, what should the unit be? Newtons. So there's something wonky here, but I like where your head's at. I'm going to just change this instead of force. What do we call this up above? There's two choices that we can use. We can use A or G. Which one do you guys want to go with? A. So I'm going to make it A sub G because we have another acceleration happening. If I were doing this problem and you don't, we can do it this way, that's fine. I would use 9.8 newtons per kilogram, and I would call it just G. But same idea. What direction does this one go? Downward, so I'm going to just make sure that that's negative. Everybody on board with that? Anything else I know? Okay, so here's the tricky part. We're accelerating upward. Now, I'm going to think this out. And this, again, this problem is contextually a little bit more challenging. Because if I were to accelerate upward at 9.8 meters per second squared, just for now, if I'm at 9.8 meters per second upward acceleration and downward acceleration, what happens with the bag? So why? So check it out. I have a bag, kind of. This is, we'll go the other way. Do you agree that this, like we could call this a bag? So right now, gravity's pulling down on this at 9.8 meters per second squared. It's not moving, but it's pulling down. Okay, right now, in order to keep it from falling, but not move up, how hard am I pulling up? 9.8. So I'm already at 9.8 just as I hold it. Do you guys agree with that statement? Now, instead of calling it acceleration, because you want to think that things are moving when they're accelerating, but it's only if it's unbalanced. So right now, instead of calling it meters per second squared, in my mind, I want to say 9.8 newtons per kilogram downward, which means I must be pinching here and pushing up then at 9.8 newtons per kilogram as well. It would be moving otherwise. Now, I'm already holding it at 9.8 newtons per kilogram. It starts going upward, or meters per second squared if you'd rather, but it starts going up more than that. So I'm already putting 9.8 newtons per kilogram upward, and I need how many more? I need 7 more. So in order to adjust for this, let's just add 9.8 and 7. Because I need to account for the fact that I'm going to overcome that force of gravity and then beat it by 7 meters per second squared. Does that part make sense? Conceptually, it's hard to pick out. And this is the first time this year that I think the challenge problem is legitimately a challenge. So it can't just be 7 because then gravity would win. I think it has to be 16.8. And then I'm going to make the note here. At 9.8, and we just talked about this so you don't have to write this down again. At 9.8 meters per second squared, it is at rest. Because we're fighting gravity. We're lifting a bag. Okay. Any other known information that I have? So how do I write that? Something is 15 kilograms. The mass M. Love it. Okay. I have all of this worked out. So, what are we trying to find? And I'll give you guys a second, chat with your neighbors. I'm going to call on somebody random in just a moment. We are trying to find something because it doesn't say find this explicitly, but it's within the problem. So I got 16.8 because at 9.8, if that's all I pulled, it'd be at rest. But we know it's accelerating how much faster than just at rest? Yep, so I'll put this here. This is just at 9.8 to say that, hey, look, we're fighting gravity, plus 7. Great question, thank you. All right, Nick and Rafa, you guys were chatting, which I appreciate. What are we trying to find? So if it will break, yes, I agree. But we need a quantity, some value that we're going to be able to find. And you might have said it, Rafa. The force. I need to know how strong is this force of lift. Because if it's less than 230, then we're cool. But if it's more than 230, then we break. Okay, so here we go. We're going to jump right in. We know what we're trying to find. We have all of our given information. Let's do our equations. Is there anything that you guys know of that relates force, mass, and acceleration? Newton's second law that says the force is equal to what times what? That is perfect. Mass times acceleration. I don't know what was actually said, but I'm sure it was something along those lines. Okay, as we go through, here's the other hard part. What acceleration do we use? So if I'm only using gravity, the question would be, if I'm holding this bag just at rest, is it going to rip? Which you've all probably had a bag rip at some point in your life, I imagine. If not, you'll get there, don't worry. You will refuse to make more than one trip with your groceries, and it will happen on a staircase somewhere in your life. It sucks. Rafi, you had an idea. So I like where your head's at. If it were just 7, and I'm going to flip this a little bit, it'd be like I were holding a bag with less gravity. Because like we have to counteract gravity. So I already have 9.8 just to hold it still. If the bag hasn't ripped yet, we're going to add some force to it though. One more big number. We have to use all 16.8 because we're doing the 9.8 to fight gravity, just to be still, and then the additional force to pull it upward. So as we go through here, I like this 16.8 number, and it's upward. So I know that this is 15, and I'm going to go ahead and do kilograms, and we have 16.8, and then I am going to make a change here, just so I can show you guys the usefulness if we had used G. Instead of meters per second squared, which is fine, you can use it, I would much rather use newtons per kilogram. No difference. But why is this maybe easier? I can already see that those are just going to fall out, which if I had done this instead as newtons, or instead of that, if I had done meters per second squared, I still get the right unit. But does anybody in here think you might look at kilogram meters per second squared and go, what? It's reasonable. Do you guys remember what a kilogram meter per second squared is? It's a newton. I would rather just cut out that logic and use this. Entirely up to you. Here's my unit game happening below the problem. Kilograms are gone, and I already saw Barsega typing this in. What's the force that we're going to exert on this bag? Can you be that, like, 10 decibels louder? 252. Exactly? Cool. Newtons. Awesome, we're done, right? Call it a day? No. You've gotten most of your points. Why didn't we actually get the answers? Or the full points? We need an answer, right? The question wasn't actually asking what is a force. It is 252. At what force will the bag rip? At 230, and we're doing this. Will the bag rip? This bag rips. The bag will break. We are 22 newtons too hard on this. Now, the cool thing about this is we could switch this problem around. An extension of this, without being super crazy, is I could just ask, at what point, or at what mass, will the bag rip? And we could do the same thing. We would just plug in 230 for our force, and then solve for mass. All we have to know is how the acceleration is acting. Okay, this is a fairly tricky problem. Feel okay or feel awful? Okay, I'm going to give you guys a minute. I want you to start an assignment, but we're going to do 2 problems right now just so I can do a quick check rather than just do them in your notes. I'd rather just see what your work comes out to. So I will give you like 10 minutes or so, and we're going to add problems to this eventually just so you're aware, but I'm going to call this homework 4.2. You know what? Let's just end because we won't get through everything today. Let's make sure that this one that I'll collect on either in class if you have it or on Monday if we want to take it home. We're going to have an easy first grade for second quarter, so everybody's going to start out with 100% so long as you do this. Homework 4.2.1. You're not going to have the whole class time, just so you know, but you will finish it, I think. Page 101. You get the privilege of doing problems 16, 17, and 18. That's it. Okay. I'm going to pause the video. I'm going to give you guys like 10-ish minutes so that you can at least identify if there's issues that you're having with this stuff. And then I'll probably wind up lecturing for like the last 5 to 10 minutes. Cool. Cool. So I will take this on Monday morning. If it's done and you want to hand it in now so you don't lose it, I'll take it now if you would really like to. But I also have no issue just taking it on Monday morning. We should all be able to start the second quarter with 100% in here. Cool. Let's continue on. Now, there's a lot of intuition that's going to go into today because you guys have lived on this planet. If anybody has ever lived in Dutch and only in Dutch or in Alaska for their entirety of their lives and you've never left the island, you might not have the same intuition. But I don't think anybody in here has never, ever left this island. This is going to feel silly, and I'm pretty sure I know the answer. How many of you guys have ever been on an elevator? Okay, cool. Everybody, I would imagine. But there's always the option that maybe not. If I were to ask about my weight, and I'm just going to say I'm 200 pounds. Let's say I'm standing on an elevator. Sorry, I'm 700 newtons. My bad. If I'm standing on an elevator, and the door just opened, and I stepped in, and I stood on a scale that read my weight correctly in newtons, and I looked down, it would say 700 newtons. If the elevator started moving upward, what would happen to my weight? Why? So to go upward, the scale, the elevator has to push on the scale, and the scale has to push on me, right? And I know that for every single force that exists, there's an equal but opposite force if I'm not like in true motion relative to my position. So the scale pushes up harder on me, and the weight goes up, right? What if it goes downward? I'll weigh less because all of a sudden the scale's moving away from me, which means it's pushing less force on me, and the scale reads a lower number. Now that'll only happen for a split second while you're in the elevator. Only while it's accelerating. Once you get to constant speed, even if like I'm going from the first to the 100th floor, for like the first second or so, my weight will go up. But as soon as I stop accelerating and I'm just constant velocity, my scale goes back to normal. Now, what we're talking about there, my weight didn't really change. Would you agree? It's the same force of gravity acting on me. I still have the same mass. There's no real change that's happened other than within this system in this frame of reference that we're in. So that idea is a weird one, but it's weird enough and important enough that we're going to discuss and define for ourselves what we refer to as the apparent weight. Okay, an apparent weight. So for this definition, we're going to use this idea of a scale because it's the easiest way to connect it and make sense of it in an everyday kind of situation. Our apparent weight, we're just going to define as the force exerted on a scale in a reference or a, I'm trying to think of the best way to word this, in a reference that accelerates. Now, context probably makes more sense than reference, but I'm thinking about like my point of reference with stuff. Cool. As we go through here, we know that it goes up and it goes down, depending on whether you're ascending or descending in your elevator. So as we think about that, I'm just going to make one more little small comment. Elevator up, which this is like my cave person language. If the elevator is up, like it's starting to move upward, accelerating upward, not just moving upward, but accelerating upward, we feel heavier. And I'm going to put quotations around that. We feel heavier. Are we really and truly heavier, though? Not even a little bit. I don't know if I have to do the other side of it. If the elevator moves down, what changes? We feel lighter. Are we really any lighter? No, it's just our whole setup going on. Now, hypothetically, let's use that example, and we're going to step one step forward. I'm just going to say if you want it, this is elevator down. I'm not going to write the statement, but if you need it, I would include it. Let's do one more fun thing. What if you were halfway up or all the way up, 99th floor, and the cable snaps. If the cable snaps and all of a sudden, what do we do inside of our elevator? So everything starts falling, right? And what would my scale read if I'm standing on my scale and all of a sudden our elevator starts plummeting? 0. We have a cable snap. We experience weightlessness is what it's referred to as. Now I'm going to make 2 little comments. First, both you or me and the scale are falling. Now we are falling, and assuming that we're not in a longer class, that has to be the end. We'll finish this on Monday. Cool. Everybody have a... The only homework due Monday is those 3 problems. Later, Raiders. Yes, miss. Oh, thank you. Got me good. Don't want to lose it? All right. Cool. Thank you, guys. All right, later, guys. Doing okay, Jimmy? Yeah. Just tired? Yeah. All right. Need anything, let me know, okay? All right. What's up, Fred? Oh, let's move that. How are you doing today? All right. Good. Any last minute push in any of your classes?
I'm doing great because I did pretty decent on the math test, so I brought my grade up because the last one was primarily bad. So apparently the next test, if you get a higher grade, Miss Husband said,
All right, I'm gonna make you guys do something really specific for me. I need both or all rows of desks moved back like 2 feet.
Okay. Like specifically 2 feet, right?
I mean roughly. I'd say just back because this close is getting a little too close. You're cool to start there, but it might be easier to start at the back. I don't really care which way you start. Morning.
Left the desk like 2 feet.
Yep, all the desks are gonna move back like 2 feet.
Right. I'll move this back a little. Yeah, maybe that one. Wait,
Sweet. Appreciate it, guys.
Pag mo sana parang kita ko
I did not read announcements first hour. Weird, so you usually do. Holy birthdays.
are there a lot of people on his birthday?
Yeah.
Oh.
Lots of them today. Happy last day of quarter 1, guys.
Yeah.
Woo!
Almost 40 minutes.
Not yet.
On Monday.
On Monday.
I was gonna do this, but wait, test.
I don't have the time to play with them.
What? You do what? Of this? wanted to have a quiz,
I guess it's
but I've been real busy.
Oh, it's alright.
I did not make a quiz.
I still feel
I'm sorry. Okay. Do you guys want to do Feelings Friday?
Sure.
Okay. Cool.
Dude, how come we're
I'm good with it.
I'll work.
Oh no.
I work till 9.
Cause like,
Everything's frozen on this computer. That ain't good.
Stop kidding.
All right. So bear with me because I got to do attendance on this computer. I did not quit recording.